Hello, I'm Channa Bankapur. I'm going to discuss my solution to today's daily challenge on LeetCode. So I'm going to discuss actually three solutions. The first solution is going to take big O of m squared n plus mn squared time and the big O of mn extra space. That's going to be a brute force approach. And the next improved solution is going to take big O of mn time and big O of m plus n extra space. Uh, and there'll be another method, which is probably the most efficient one. That's going to take big O of m and time and big O of one extra space. So I'm going to discuss all the solutions like one after the other. Let's start with the first, a brute force approach. So what could be a brute force approach to this problem? The problem is we have a matrix of order m cross n. And so if an element is zero, we need to set its entire row and column to zeros, right? And we need to do it in place so that the given matrix is going to be transformed essentially. But let's not worry about whether we have to do it in place or not. So what do we need here is the source matrix looks like this, and the transformed or the resulting matrix should look like this. And the idea is wherever there is zero, we need to basically zero the whole column and row, right? And there might be multiple zeros in the original matrix, which is kind of, we can see that in the example too. So in this case, row zero has two zeros, but the effect is still the same. All of them, the whole row zero is going to be zeroed. And column zero and column three are also going to be zeroed because of those zeros, right? So a brute force approach is basically you take a copy of the original matrix, and whenever you see a zero in the original matrix, you basically zero that row and column in the resulting matrix, which is a copy, right? And because they want to do it in place, you can copy them back to the original matrix in the end, and then return, right? So why does it take big of mn squared plus m squared in time? Let's see the solution. So here is a solution which should look much simpler. The order of the matrix is m cross n, which is captured that in two variables. So now for every, I have a temporary matrix, which is going to be a copy of the matrix to start with. And for every I comma j, so the first two loops is going to basically get you for every I comma j. This itself is going to take big of m and number of times, right? Let's see what happens inside for each I comma j. If that matrix of I comma j element is zero, that means the row I and column j needs to be zeroed out. So that's exactly what I'm doing. If a matrix of I comma j is zero, uh, in this case, this is column J. So the whole column J I'm zeroing out in the resulting matrix, which is this temp matrix, right? So that's why I have another loop index called I2, which is going to be the row index, but the column index is going to be J itself. That way I'm basically zeroing the whole column J. Similarly, I'm going to zero the whole row I also. So using another loop index called J2 for all the columns, right? So this itself, the internal, this body of this loop is itself is going to take big of m plus n time, right? Because we have a loop which runs for m time, and then another one which runs for n number of times. So that is very clear to me. The overall time complexity of this whole stuff is going to be big of mn times of m plus n, right? So which can be written as m squared n plus mn squared, right? So this is the time complexity of this method. And because we are using a temporary matrix here, which is going to be a copy of this, and that will take big of mn extra space, right? And we are copying it back to that. Even though these two instructions itself actually are going to take big of mn time, but uh, they're not significant, or they're not superior to this number already. That's why the time complexity ignores those two operations, right? So this works, but how do we improve from here on? It takes cubic time and quadratic extra space. So what we need here is, so the redundancy here is whenever a row or a column has multiple zeros in the original matrix, we run through that the whole row multiple times to zero it out, even though it is unnecessary, right? So we do that here. We zero the whole row or column whenever we see one of the zeros there. Actually, for each zero we see, we are going to do that. That is redundancy, right? So instead, we can just remember if that row needs to be zeroed out, and then in the end, you can just zero it only once, right? That can be done. So that's how we can remember for every row and column whether that needs to be zeroed out in the end, right? So that's going to be my second solution. So here is how it works. So I'm going to have vector called rows, where it's a bool vector for each of the rows, whether it needs to be zeroed or not. So to start with, it is false. So I don't need to zero any row, but I'm going to go through every I comma j and then look at matrix of I comma j element. If that is zero, that row I and column j needs to be zeroed out. So those are the two things I'm going to remember here, right? So now once I'm done with this, this is only going to kind of, remember which rows and which columns need to be zeroed out. We haven't actually modified the matrix at all. So now I'm going to do that. So I'm going to go through each of those rows, which is basically a bool vector called rows. And if rows of I tells us, ith row needs to be zeroed, I'm going to zero this ith row. Similarly, I'm going to do it for each column also, right? So look at this. What is the effort? Uh, this whole thing takes big O of m in time, because for each element, we are just noting down whether ith matrix of I comma j is zero. If that is the case, we take constant time to remember, row I and then column j to be zeroed out. And this code also in the worst case takes big O of m in time, because for every row, if that row needs to be zeroed, we need to basically zero the whole row. That itself is going to take linear time, or it's going to run through all the columns. So that overall is going to take big O of m in time. And this will also take big O of m in time. So put together, it's 3 stages. So it is overall still big O of m in time. And space-wise, we have this, two vectors here, which one of them is of order m, another one is going to be n. So that's why it is going to be big O of m plus n extra space, which is better than the previous solution. We are actually, we have improved both time and space. Time, it was cubic there, and then we brought it down to quadratic, and the extra space was quadratic there, and then we brought it down to linear, right? So it is definitely an improvement, right? But yeah, is there a possibility of bringing the extra space down to big O of 1? So why am I not thinking about bringing down the time complexity here is, see, big O of mn is the lower bound time complexity for this problem, because the matrix already has big O of mn number of elements in that, right? And anyone could be zero. Like without looking at each of those elements, we cannot decide, right? So in the worst case, we may have to look at every element. What if there are no zeros? Just to search for if there are any zeros, we're going to take big O of mn time, right? That's why this is the best we can do in terms of time. Space wise, right now we have big O of m plus an extra space. Can we bring it down to big O of 1? That is my effort right now. So is there a possibility of whatever this rows and columns vector, whatever we are doing there, we are remembering a row and column needs to be zeroed. Can we do that job without actually using these extra vectors? Can we use that first row and first column for the same purpose? Right. So it turns out we can, but not in a naive way, because whenever you suppose you take an example again, let's go back to this example. Maybe the first example, let's look at it. Our first example doesn't really capture the idea. Let's look at the second example. So okay, even there also only the first row has zeros. So I'm going to modify the second example a little bit and see if I make this 5 as 0 here in the original matrix. So now if I capture the idea of which rows and which columns that needs to be zeroed, so I'm going to get a 0 here and a 0 here, right? What if these original zeros are not zeros? They are like non-zero, some non-zero values. So we had only 1 0 originally in the matrix. So this is how probably it looked like. There is only 1 0 in the original matrix. The resulting matrix was supposed to be like only zeroing out this row and this column. But if I remember, the first row to be zeroed is this, and first column to be as in first, this row needs to be zeroed and this column needs to be zeroed. If I just remember this information, so it's going to zero out this row and this column, right? So that works out okay for now. But what if the original matrix had 0 here also in place of that 2? So now when I mark the first 0, which is going to be a 0 here, because of 5, we are going to mark these two as zeros, but we don't know how to remember the first row to be actually zeroed, because that needs to be zeroed because of the original 0 here already. So that's why I need some other information, like the first row and first column, whether they need to be zeroed or not is something we need to remember different in a different way. So what if I remember them? Because originally, if the first row is 0, so I'm going to say, oh, the first row needs to be kind of, needs to be zeroed. So I'm going to mark it as some kind of true there. But in this example, the first column does not needs to be zeroed. So I'm going to say first column is going to be like false. So this takes constant extra space, right? But it takes linear time, let it. But yeah, we take constant extra space. Now, after this, the first row and first column are kind of, free for us to be, used, right? So we can parse through the rest of the matrix, excluding the first row and first column. And wherever we see 0, if we see 0 at I, comma j, we can mark the ith column and ith row and jth column in those first elements. So how do I mark ith row is going to be, I'm going to look at ith rows, the first column's ith row, which is going to be I, comma 0. So I'm going to reset it to 0. And then similarly, 0, comma j also should be reset to 0. So they are going to be our markers for, zeroing the whole row and whole column there. So, and once we are done with this parsing, we can go ahead and then zero those rows and columns. And after everything is done, we look at these two variables and see whether the first row and first column needs to be zero, right? So this overall in every stage, either they take linear time or they take quadratic time. None of them takes more than linear or quadratic time, and there are a constant number of stages. So overall time complexity will not exceed big of m in time. But space wise, we didn't use anything more than big of one extra space. So that's why the space complexity is going to come down. But it's a little bit a harder way of coding than the previous solution. Let me show you that. Yeah, so look at this. I'm using something called row flag and then column flag to indicate whether the first row needs to be zeroed and first column needs to be zeroed, right? That's the purpose of those two variables. And I'm going to set them right here. So I look at the whole of the first row here. If there is any 0 there at some point, this is actually for the first column. So I look at the whole of the first column and I see if there is a 0 at some I, comma 0, then that, I'm going to set that flag, column flag, which is the first column needs to be 0. So I just need one of the zeros at least. So as soon as I find 1 0, I'm going to break out also. So I'm not even going to go through the whole column. Similarly, I'm going to go through the whole of the first row, and then if I see a 0, then I'm going to set this row flag to be true, right? So this is done for now. And now this is the core part of it. I go through every element of the matrix I, comma j, excluding the first row and first column. That's why I look at the indices are starting at 1. And whenever I find a 0, I'm going to basically mark the first element in that column and first element in that row as zeros, right? Which is what we wanted. When I, comma j is 0, I, comma 0, which is going to be the first element in that row, ith row, and 0, comma j, which is going to be the first element in that column, jth column. Both of them are going to be reset to 0, right? These are more like markers for now, because this indicate that row and column needs to be zeroed, which we are going to do it in the end, right? So that's why this whole thing takes only big of m in time, no extra space. Now, once we are done with this, we have all the markers set. We just have to kind of, go over and set those rows and columns. But yeah, we don't have to go over the whole matrix. We have to go over, the first row and first column. Look at this. I'm going over the first column here. First column as in the column index is 0, but the row index is going to be from 1 to n, right? So in that case, if it is a 0, that indicates that whole row needs to be zeroed. So that's why that ith row needs to be zeroed. J is running from 1 to again end of that row, and it's going to zero out that whole row. Similarly, I zeroed the columns that needs to be zeroed out. Once we are done with that, then we have to go back to that row flag and then column flag. They only serve that purpose of whether that first row and first column needs to be zeroed, because they were used for some different purpose, right? The numbers you see there are not going to be like, you cannot depend on them. So now if the row flag is set, that essentially means the first row needs to be zeroed, right? All 0, j needs to be set to 0, where j is going to be from 0 to the end of that row. Similarly, the column, the whole of the first column is going to be set reset to 0 if column flag is true, right? So if you observe what happens with respect to time and space, you can easily see the only extra space are constant extra space, m, n, and then these two flags. So all of them put together is constant extra space, right? So big O of 1 extra space. What about time? Okay, let's look at the first loop. This takes big O of m time, and this takes big O of n time, and this takes big O of mn time. This is going to be big O of m and then again n, so mn. This is also big O of n and then m. So this is big O of n and big O of m. See, we have multiple stages, like 7 stages here, and all of them take more than some constant time, right? But if you add up all of them, the significant parts are going to be big O of mn. So the overall time complexity is going to be big O of mn, right? So this is probably the most efficient solution, or the lower bound solution, I would say. But yeah, so if you really are interested only in the time, maybe the solution 2 is already good. It takes big O of mn time, only some linear extra space it takes. And look at the number of stages are only 3 here, not like 7 in this case. So it should run. So I have written all of them, all of the solutions here. All of them are acceptable. Actually, I have tried that out. So, but and LeetCode test cases are not that robust. So we won't be able to figure out by looking at the runtime. But yeah, all of them are acceptable. Right, so accepted here. All right. So I'm sure there are other solutions, like, there is definitely a solution which where you can use some hash table to remember which rows and which columns need to be reset and things like that. So some of them could be better than the solutions I have explained. Let me know if there are any interesting solutions, right? Otherwise, keep solving a problem every day. Thanks for watching.